Okay, so we were discussing about memories, and memories are classified into two main categories: volatile and non-volatile. And these volatile memories are ones that only remembers data whenever power supply is available and it is turned on. Whereas non-volatile memories are permanent kind of memories where the data stored in the memory is remembered even if power supply is turned off. And power supply means always DC power supply for memories. So volatile memories are some sort of temporary memories, or you can say secondary or prime, depends on how you are applying it, secondary or primary type of memories. I will tell you about that also. At this stage, just remember, volatile memories are something like RAM, random access memories, and non-volatile memories are something like flash or ROM, read-only memory. So we'll very quickly overview different types of memories that are used in embedded systems. So first, the non-volatile memories. So these are different types of non-volatile memories, and non-volatile memories are also sometimes called as read-only memories, because non-volatile memories may not be always erased based on the original definition of non-volatile memory. So non-volatile memory should be only programmed once, and only one time programming memories, but you can do reading millions of times or many times afterwards. So those kind of memories were originally termed as read-only memory, ROM. So that means only one-time programming. So you just almost ignore the writes operation, and but writing is important. But later on, you cannot write it back. So that's why it is called as read-only memory, because all the time you are reading. Most of the time you are reading, and these are the different types. Although some of the types, like the first two types, are almost obsolete these days, but evolution of memories in this category came out in this form, that programmable read-only memory. So PROM, that is means one-time programmable memory, but many times read, as I said. So this is almost or totally obsolete. Actually, you won't find it anywhere in any devices. Then something around 1980s and early 90s, this EEPROM became more popular, which is called as erasable programmable read-only memory. Now, more closer to RAM, but still non-volatile memory. Erasable, you can store once and you can read it many times, and if you need, so you can again erase the content of the memory and then store it. These days, we really don't use this memory anymore again. This is another obsolete type of memory, erasable programmable read-only memory. So people used to use ultraviolet light to erase the content of a memory in this EEPROM category. So you may search through internet with this EEPROM term, you will find the photos of different integrated circuits with some round window, something like a little glass window on top of your chip, and that glass window, through that glass window you can see the actual integrated circuit inside the chip, and the glass window was used to shine ultraviolet light for certain time, certain intensity, with certain intensity, such that you can erase the content of the memory. And if you need, such as if you have a mobile phone now, if for erasing or deleting something, if you need an ultraviolet source, that is very inconvenient. So people came up with even better solutions, that is EEPROM, electrically erasable and programmable read-only memory. So this EEPROM means just it replaces the optical method of erasing. Rather, it can do erasing or deleting of the memory contents by using simple electrical pulses, something, a combination of voltage and current. So this was a major breakthrough during late 80s, early 90s kind of thing. This was a topic of research at that time. Now, EEPROM memories are there in many devices, including your handheld remote controls for your television sets. Suppose in your TV set, you take your remote control and you have set certain brightness levels, certain contrast, certain selection of channels, or certain preferences on for your television. So those preferences are used, or rather stored, in the EEPROM memories. So EEPROM memories are still in use today, very widely used. But those memories are serially accessible. Again, that's interfacing details. So EEPROM memories are used to store certain user attributes or user preferences or selection for your device. For example, apart from remote control, suppose you want to use your mobile phone, but with certain brightness and all those things, as I say, display preferences or carrier selection preferences, those are also used in certain older mobile phones. But in the newer mobile phones, we use flash memories. Flash memory is a type of non-volatile ROM, you can say. Flash means it's a type of EEPROM, in fact, but here the number of delete and program cycles is much better or much more than EEPROM. So EEPROM and flash memories, they are very close by. Both are electrically erasable, electrically programmable kind of memories, non-volatile memories. But flash can be programmed many times, or much more number of times as compared to EEPROM. I'll give you an example. EEPROM, in this traditional form, people were used to delete only 100 times. That means you don't change, if you change or delete the content of memory more than 100 times, your memory will go useless. Rather, it cannot store subsequent data. Whereas in flash memories, it came up with 1000 kind of cycles, write, delete, write, and then whatever number of read cycles. So delete, write cycles is called endurance of a memory. Okay, you can note down this term, endurance of a memory. Endurance means number of write, erase cycles. So that write, erase cycles, the endurance of flash memories is typically very large. Now later on, EEPROM also advanced to more than 1 million, and flash has also advanced more than hundreds or tens of millions these days. So that's why we can delete any number of images and songs and videos from our mobile devices and again store back. We don't care how many times we are deleting, because the endurance of the flash inside our modern memories is really very large. And by that time, the memory will go useless, and before that, you will possibly change your phone.
Sir, is the
Yeah.
EEPROM faster or slower than the flash? Because we do find both of them in today's microcontrollers. For example, Atmega 328P,
Mhm.
we have flash for programming your uh, code memory, but you can also use EEPROM to store things. So if both
Yes.
exist, what is the
Yes. So with the modern memory technologies, actually the memory technologies have evolved to an extreme level these days. I can tell you something more about different memories that are used in various microcontrollers. For example, your question is very valid. For the Atmega, or basically Aviar kind of microcontroller, that's the RISC microcontroller, we have used, basically, as you said, there are two types of memories, but it depends on which technology they have used. If you look at the data sheets, as far as I remember, they don't say much about the internal technology of a memory. Okay, so that there are different fabrication strategies and there are different physics behind the modern memories. But the EEPROM is typically used to store user data. For example, something that will refer to many times. But for flash memory, as you said, it is mainly used for code storage. Now, the endurance of these two types of memories depends on the fabrication strategy. So, if you look at the datasheet, they must have said about the endurance, like 1 million cycles for EEPROM, or
yes,
maybe
they do. Yeah, yeah. 10,000,
and
100,000 type for the EEPROM type. But
Yeah,
my
so
point is
whatever
like, why
number.
do you have an EEPROM anyways? I mean, it must give some advantage, right? Otherwise, I can also store it in Flash, user data.
You can always store it flash. In more modern microcontrollers, you don't have EEPROM, you have only
Okay.
flash. Okay, but for Atmega, so this is slightly older variant of the RISC microcontrollers, 8-bit space, where you can store the user data. As I said, suppose in your remote control, you are using the microcontroller for, let's say, controlling a robot remote control, or a drone remote control, for example. So in that, so you must be storing some user data, such as what should be the RPM of each of those motors, what should be the accelerometer readings for stabilization while it is in the air or while it is taking up and just coming down to the ground. So those kind of user data, user specific data, are typically stored in the EEPROM. So it's EEPROM typically stores the data, but the data that will come to it again and again. So if you store it in RAM, it will forget, obviously. But if you store some user data which will access again and again every time you turn on the drone or whatever, then the EEPROM is the preferred memory location where you can update it many times. Now the coming to the advantage and disadvantage, flash memories are typically erased in segments or in page. I mean, segments and page means you cannot delete one memory location, one byte location from a flash memory. Whereas, if you want to store, let's say, some 10 or 15 bytes of data, you don't want to delete 1024 bytes of data and then update all 1024, but only 10 are new data out of that. So that is very inconvenient for flash, and also that affects endurance of flash because you are losing one write delete cycle. For EEPROM, you can access one byte at a time. So that is another advantage why aviar people thought that EEPROM could be used. But modern days, as I said, with MSP 430, for example, there is no EEPROM, it's only flash. And one reason being, there is a large amount of memory typically available, not in all microcontrollers, but many. So in those microcontrollers, even if you can reserve one page of a flash, that means let's say 5112 bytes or 1024 bytes. So you just keep that 5112 bytes of space or page, or even segment also some people call it, depends on how it is organized internally. You have can delete those 5112, but don't write any code within that 5112 bytes. So you have, if you have adequate memory, then you can afford to sacrifice one page or one segment of a memory for data. But for EEPROM, typically you can access one byte at a time. So that is the main advantage of EEPROM. That's why it is still in use, as I said. Is it answered? Is the
Yes, sir.
question?
Yes, sir.
Okay.
Yes, sir. Thank you.
Now, next come to the RAM or volatile kind of memories. So the volatile memories are of different types again. The most traditional volatile kind of memory is static RAM, SRAM. SRAM is the RAM that is used in modern microcontrollers in the embedded space. Static RAM is very popular because of its low power operation and very simple circuit. There are only 6 transistors. You can read that separately. So in a given bit, again, RAM locations are required to be powered all the time if you are using it. If you stop it or power supply is disrupted, your previous data will be automatically deleted. So static RAM means if you store the data, it doesn't forget until the power is switched off. So that means the data becomes stationary or data becomes static. So it doesn't change. You don't have to apply any clock. You don't have any control over it other than power supply in static RAM. But in dynamic RAM came up later on, which is actually much faster than static RAM. As I said, there are 6 transistors in SRAM, but in contrast, the DRAM has only one transistor. So there is a huge difference. That means 6 is to 1. reduction in size. So if you take any technology, VLSI technology, 180 nanometer or 65 nanometer or even 22 or 7 nanometer these days, 5 or 7 nanometer these days, you just think that accommodating 6 transistors and their connections in between versus accommodating one transistor and its necessary connections. The space is significantly reduced. And if you have a reduced space on chip, although these are in micrometer square or nano hundreds of nanometer square or even few nanometer square, depends on size of the technology, 180 nanometer or 7 nanometer. The size of DRAM per bit is extremely small as compared to SRAM. But that's not all. DRAM chips are quite fast in the sense that you have less number of connections. That means less number of capacitors in between. So in the VLSI lab, we will talk about capacitance in different circuits that we generally don't consider, or you may not have considered so far, as a load. So whenever there are more connections, more interconnections, the interconnections means what? Some metal connections, and those metal connections inside an integrated circuit are very close to each other, and those close metal lines form parasitic capacitance in between. So if you have less connections, less transistor, obviously less capacitance. As a result, your speed improves, because if you have smaller capacitance or less number of capacitance, automatically your chances of the time constant to be low is becomes really dominant or predominant. So DRAM offers quite fast operation, but it depends under certain conditions. If you compare with SRAM in speed, but in space, DRAM really wins. Now, the third type, NVRAM, which is the very latest one, in very few embedded microcontrollers offer this. They offer NVRAM. So NVRAM is non-volatile RAM. Now I said RAM is volatile, but NV is non-volatile by name itself. So NVRAM actually breaks the barrier of the RAM and it goes to the non-volatile space. So it's a type of RAM which can be read and even write erased for millions of cycles. See, for the SRAM and DRAM, there is no limit of number of delete and number of write cycles. It is virtually infinity. So if you have power, if your chips are good in quality, in terms of fabrication quality, I mean, then you can read, write, delete millions, even trillions in whatever else, zillions of time for this SRAM and DRAM. Only it will take some energy to do that and time to do that. But for NVRAM, it is more like flash memories, but it is also having some characteristics of EEPROM that we discussed in the previous slide. So as I said, EEPROM is byte accessible typically, whereas flash is page or segment accessible. That means group of memory should be deleted for flash, but reading from flash could be done byte by byte. So reading from any memory is possible byte by byte or word by word. That means 16 bits at a time or 32 bits at a time. So all these advantages of all different memories, right from non-volatile to volatile space, are actually solved in NVRAM. So MSP 430 is one of the microcontrollers that's featured this from Texas Instruments. So there is something called ferroelectric RAM, FERAM. So that is a type of NVRAM. So there are some magnetic nanoparticles used inside the RAM memory architecture that helps to get magnetically polarized, and that forms in non-volatile data retention. That means after powering off, your RAM will become basically will still store the data, and if you power it up again second time or next time, you can retrieve the old data, which was not possible with DRAM and SRAM. So NVRAM virtually provides infinite write delete cycles as supported by SRAM and DRAM, but also it retains data even if power is off. That means it's similar to flash or EEPROM, and also it is byte by byte addressable for write and read operation. So that is another characteristic of that non-volatile EEPROM. So it combines the all advantages of flash, EEPROM, even SRAM, DRAM. One thing I just wanted to mention for DRAM, dynamic RAM, why it is called dynamic RAM? Dynamic RAM means basically it requires certain time to time refresh operation. That means DRAM, if you store something in DRAM and then if you forget to replenish the charge, it will forget the data. I repeat actually what I mean, maybe confusing. I have one transistor and one capacitor in a DRAM. Okay, think of one transistor in source follower mode. Remember source follower mode in from analog. Source follower mode means the drain of the n channel transistor is connected to VDD and the source of the n channel transistor is driving the load, resistor or capacitor. Here the load is capacitor. Now, if you turn on the switch, that means the MOSFET, your capacitor will get charged up. If you turn off the switch, your capacitor will retain the charge. Now, the point is the capacitors, on-chip capacitors are so small and they're also leaky in nature. Leaky means the capacitors are not ideal. They actually lose the charge if you don't recharge or top up the charge. So it's like you are storing some charge in the capacitor in source follower mode, and then if you don't recharge it after some time, your capacitor will automatically discharge because of its internal leaky nature and very small capacitance. Obviously, after some time gap, if you read the DRAM value, DRAM will forget everything. So that means your data is wrong. So that's a problem in DRAM. So to combat that, there is a refreshing. So that means dynamic updation is happening. It's like your mobile phone battery is all the time discharging and you are time to time recharging. The same analogy works at a much faster rate, obviously, for DRAMs. But at the same time, DRAM takes small space, so that is huge advantage, and that's why it becomes so popular. And there are different generations of DRAM. DDR6 is available commercially these days, which are used in graphics card. So DDR6 are very, very fast and quite low power. And also it operates at low voltage. So that's why DRAM become extremely popular. But inside the microcontroller, typically you will find SRAM. Another observation, because SRAM doesn't have that refreshing overhead. You just store and forget kind of thing, and you come back whenever you later on. If the power is on, it will give you the correct data. So that's the advantage of SRAM. Obviously, there are advantages and disadvantages of each and every one. So NVRAM is very expensive these days because it uses magnetic nanoparticles, and that too within the transistor, basically within the integrated circuit. That's a very complex technology. Everyone cannot do that or manufacture that.
Sir, SRAM also has capacitors, right?
Yeah, so all capacitors are having it. All memories are having some sort of capacitance, but the role of capacitance in DRAM is very profound. If you don't recharge it or refresh it dynamically, periodically, it will lose. Yeah, but capacitance are there for all memories, even flash and EEPROMs, and that restricts. That's one of the reasons that restricts the speed, the maximum speed of operation.
Then why doesn't the refresh operation come in SRAM?
Because in the architecture, it's like a flip-flop. SRAM is like a flip-flop, like a D flip-flop, you can say. So whenever you store something in through the D flip-flop by applying D and Q as D and clock. So what is D flip-flop? You apply 1 to D and then clock signal. Your Q output Q will be updated with 1. And if your clock becomes 0, the D flip-flop will still keep that logic 1 at the output Q, right? So D flip-flop is like SRAM, or SRAM is like a D flip-flop, you can say. But architecture circuit-wise, it is slightly different because of reasons. Whereas you understand this analogy, so you don't have to basically restore the data in SRAM. It will just keep on storing unless you apply another clock signal to it. But in SRAM, we don't call that clock, we call that bit line, word line. So, and also there is a differential readout. So again, those are memory design details actually. You can study SRAM architecture in 6-transistor SRAM architecture, which is the most traditional one. Okay. So just last point actually, this data storage, basically volatile memories can also be used for core storage as a secondary application. That means in certain processors, your code or instructions could be in the flash or whatever memory, hard disk or any other memory. And then for speedy operation, for faster operation, you can bring a part of the code and store it in SRAM or store it in DRAM and then execute from the SRAM or DRAM. So that is also used for one use case for volatile memories for improved speed, because every time you go to flash memory, it takes slightly longer time because flash memories are different in the sense that they have a different type of transistors used in flash. You will possibly study that in VLSI engineering with Professor Gaurav Datta. Okay, so flash memory technologies, all these memory technologies are very, very interesting. You will find lots of very intelligent ideas, very interesting ideas used. Now for the memory map, so I'll just quickly go over it. Details will come with actual microcontrollers. Memory can be mapped or organized in certain ways. That means it's like organizing your house. So you have furnitures, you have gadgets, you have different other utilities at your home. Now you are asked to tidy up. That means you arrange the things, some guest is coming and you want to tidy up. So what you will do, you will basically think how you should organize for better space management, better time management, and so. So you have to make some logical arrangement of your utilities at your home. Same or similar requirements are there in memories, and we call that a mapping of memories. That means we arrange different location of the memories for various purposes. Suppose a sitting area should be there in the living room. Sofa should be placed only in the living room, not in the bedroom, for example. So you are doing organization. So you are doing arrangement or mapping of space. So particular space allocated to particular use. Space could be in memory as well. So the total space of a memory, for example, if you look towards the left, is called as address range. So that is the total memory space that I have. From 0000, these are in hexadecimal numbers, until FFFF. This is again in hexadecimal. So that means 0th location to 65,535 65,000 535 55 locations. Sorry, 565 locations. So there are 4 nibbles here. That means 4 digits here for hexadecimal. So 2 to there, that means there are 16 bits. So 2 to the power 16 locations, whatever is that number, 65,005, I think 35 or 55, whichever number, you can just put 2 to the power 16, and corresponding hexadecimal number is FFF. Okay, so this is the total space that I have in my house, for example, in my memory, called as address range. Now within that, I split it into various purposes such as EEPROM or flash or EEPROM or whatever other type, NVRAM. Then there are some registers. Registers, as I said, stays within, very close to the microprocessor within a microcontroller. These are small memory locations. Then RAM chip 1 or RAM space or page 1, that means some part of the RAM, another part of the RAM in RAM 2, another part in 3 and 4, and so on. And there could be registers even splitted in between or at the last or at the somewhere in the middle. But typically there are certain rules over here. The first rule is that 00 onwards or 0000 onwards, we prefer to keep the programs. So programs are stored in flash or EEPROMs. or different other non-volatile memories. So program space is first used from 0 onwards. Now your program may have some size, and after that you keep on storing other things after the program ends. Now how much space is required for program? That depends on your application. Typically microcontrollers offer you certain memory space like 2 kilobyte, 8 kilobyte, 32 kilobyte, 1 megabyte. Those kind of memory spaces allocated for flash or non-volatile code storage. So that is reserved from 0 onwards. But this notion of 0 onwards for code actually breaks in certain microcontrollers. I cannot say that this is true for each and every microcontroller. It is true for most of the microcontroller, many microcontrollers, which are in the 8-bit and 16-bit space. Even certain microcontrollers start the memory, this code space, somewhere after 0 in between. And what it does in the first few locations, it stores something similar to BIOS in computers, in basic input output system. So there is a BIOS chip inside our desktop or even laptops within the motherboard, and that kind of BIOS like information, which is system level or low level hardware information. Low level means not really low and high that we mean in general. Low level means nitty gritty level, detailed hardware information. So that's what in embedded or computers we call low level information. That is binary level information or system level hardware configurations or very intricate internal details of hardware, like MAC address is a low level information or low level setting. But IP address is relatively high level setting. So
Does this
those
also
kind of low level settings are 0 onwards in certain microcontrollers. Yes, question?
does this also include the vector table and those things?
Exactly. So there are some vectored interrupt tables are there. There are vectored different types of service tables are there, and also where this RAM1 starts, where this RAM2 starts, and so on. Those kind of information are also stored in the first few locations. So some people call it vectored memory location. So actually, vectored memory location is a bit confusing thing, but vectored information is rather, I'll say, generalized way of looking at things. Vector means some location or some point in the memory. In memories architecture I'm talking about, vector means some location in the memory in between, and then from that onwards, whether it is in the lower side, let's say 5FFF, so I can start the first location from here and go on storing on the upper side, or keep on storing in the bottom side, right? So the vector is basically the direction and the value from which it starts. So that's basically vectored information that could be stated in general. Okay. So, but in 8051, so such basic input output or BIOS like hardware information or this kind of mapping information is not stored. We have this kind of mapping or basically distribution of various range of locations in the memory by the programmer, and that should be considered while writing the program inside this first few locations in the address range of for the flash memory. Now you may not have so many RAM chips. You may have just one RAM chip, or you may have just external whatever number of chips, but internally there is only one set of locations. Certain microcontrollers help you that, let's say, RAM1 set of locations are inside and RAM2 locations could be off chip. So that means this is not inside the microcontroller. So you may connect or don't connect this area, but this RAM1 location may be always present. So that is one possibility. And in certain microcontrollers, so you can say that, oh, you don't have the option for RAM1 and 2, but RAM2 onwards, but you have only internal RAM1 until whatever space in between. But the space occupied by RAM1 must be within the address range. So address range is the ultimate boundary over which your memory should be present, including non-volatile and volatile memories for code and data storage. And within that address range, you have to split up. These are basically, you can make different rooms. You are given with a big apartment without any walls in between. Now you can create partitions and make rooms of different sizes. And in certain cases, it's not necessary that only memories are present within the address range. So that is another important thing. IOs, input outputs, can also be present within the address range. That is very common in microcontrollers and embedded systems also. So you will see that, we'll come across that with real examples. So IOs may also be present, but those are called memory mapped IOs. We'll see in detail, and there could be other types of devices, like there could be external communication devices within the address range. So that is also categorized as input output. Now in this slide I will explain a generic architecture of a microprocessor, and microprocessor is sitting within a microcontroller. Okay, so we have studied memories to some extent. We have an idea that memory is something that acts like a supporting device for the microprocessor for storing data, either code data, program data, or user data, like information like song or whatever. But what is there inside a microprocessor? That's also something I told you in one of the slides earlier, that the microprocessor fetches instructions one by one. It decodes as it goes on fetching. After fetching, it decodes. That means it understands what is the instruction, what is the meaning of the instruction, and then it executes, it serves the purpose. Okay, so these three things, fetch, decode, execute, are always going to come in if you look at the details of any microprocessor. So this concept came from microprocessor, and that is explained, or rather stated over here, that how it performs that: fetch, decode, execute. Okay, so this fetching of some code or data from memory, so that must be done. So that means from the memory, and memory is typically outside the microprocessor area. If it is a microcontroller, it is within the same chip. Memory, microprocessor within the same chip, but outside the microprocessor boundary, it may be on the same chip. Like there are many families staying in the same building, but those are different families, right? So same thing, memory is the one family of circuits, and microprocessor is another family of circuit, all staying within the same building. Now within the microprocessor family, or within the microprocessor system, what are the things? You have to fetch data from the memory. That means next door, you have to go next door, knock it, and then get the data. So how do you do that? You first provide address through the address bus. Address bus is outside, looking outside from the microprocessor, and it looks inside the memory. So address bus carries the address, which memory location, from the address range that we discussed last time in the previous slide. Now from there, you have to basically get the data. So data from the memory will come from data bus or through data bus, and through the control bus we will control whether it is read operation or write operation. So memory will understand what the microprocessor is trying to do. Now how it will generate control automatically? It will be generated by basically, initially the microprocessor will start itself. It will take the initiative to bring in some data after you power on. That is automatic, and that is programmed, or rather hardware programmed. It's not software program. So first time you power on a microcontroller or processor, it is hardware programmed. That means the connections are done in such a way, such as the counter. So if you start after power on, you start a oscillator generating clock, and then there is a counter, and the counter location 1 will do something, counter location 2 will do something else, counter 3 will, or location 3 will do something else, and so on. That is called hardware programming for a particular function. So once you start the microprocessor, it will issue the first address like 0000 on the address bus. Then it will issue read signal on the control bus, because you don't have any data so far. you have started newly, and then whatever data the memory will provide, it will come through the data bus. Now look at this. So this internal vertical line is very complex, and each line doesn't mean one single wire. Here each line represents multiple wires. It may be 8-bit wide, it may be 16 or 32 or 64 or any other um, width, standard number of lines which are common and going to many places. So it's like a highway. So there is a multi-lane highway, and through the when the data comes, where it should go, that is again controlled or hardware programmed inside the processor. So data has come to this bus and it is lying there and everything is connected. Look at this. So that is a bit confusing. Now this control circuit, the timing and control is not for outside, it is also there for inside. So that means this control, timing and control is used for all internal blocks. It will determine where the data should go. It may go to registers, it may go to instruction register, it may go to any other locations. In fact, there should be one line over here also. I forgot to keep that because data bus is connected to instruction register as well. So we have started the microprocessor first time, data has come, and I will prefer, or rather the microprocessor is typically programmed to keep it in the instruction register first because 0000 was the address, and at that location we must have the first instruction. That instruction may have subsequent data for in subsequent bytes, that is separate, but the first location should have the instruction. The first instruction has come from the data bus. Instead of going anywhere else, it will simply come and sit in the instruction register. That means the memory content gets copied to the instruction register. Memory is read and instruction register is written. So instruction register is inside the microprocessor, and this register can be anywhere within the address range. That is possible, or it may be even outside the address range, implemented separately. Implemented separately means it doesn't come in this range of address, but it may be accessed in by some names or some other methods of addressing. So there are different addressing schemes also. This is the most simple addressing scheme that I showed. So the first instruction is sitting in the instruction register, and then you have to decode. So you have fetch the instruction. So fetch, decode, execute are the 3 steps we wanted to do. So we have just fetched the instruction in the instruction register. After this fetching, I have to decode. So that is done. You can understand possibly by now that instruction decoder is there. So instruction decoder will take the value, whatever data has been just written in the instruction register from the memory location 0000, that gets decoded. That means the microprocessor is trying to understand what is the meaning of that instruction data or instruction value that came from the memory. So decoder in case of microprocessor is very large, in the sense that what is a decoder? If you remember digital decoder, 2 to the power 4 decoder. That means there are 2 inputs, 2 to the power 2 times, 2 to the power 2 times, or 2 to the power n times output. Decoder always has minimum input lines and 2 to the power n output lines. Okay, so similar thing in instruction decoder, such large decoders are used, like 8 is to 2 to the power 8. That means 256 possibilities of outputs are there. So such a large instruction registers are instruction decoders are used. That is a huge decoder has been constructed inside, and assuming the data bus is 8-bit, like in AVR or 8051, and that 8-bit data is sitting in 8-bit instruction register, all 8 bits are now decoded to 256 outputs, and out of all 256 outputs, only one output will be activated based on the value here, because there is only one single digital value. Considering all 8 bits together, there will be one binary value, obviously. So that binary value will correspondingly activate only one output of the instruction decoder. And then this timing and control unit will try and track which output of the decoder is activated, and that particular output must be asking for something else at the next step. So let's say the instruction, the first instruction value that came, that has an adjacent value, like at 0001 in the memory location we have read 0000, let's say some value, and then at 0001 the next second location over here must be a data which which is required, for example, as a part of the first line of this instruction or program. So what it will do, the timing and control requires the second byte information as well. So first byte has come and we have decoded it, but second byte is also required before starting the execution, for example. For that to happen, your timing and control will say a program counter. This is, look at the name, counter. Counter will increment or decrement, and program counter means it is only trying to point to the program space in the memory. So timing and control will say to the program counter, you increase by 1. You were originally 0000, increase it to 0001 in hex, and then apply it to the address bus. So timing and control will say that to program counter, it will do, program counter will serve the purpose, it will increase and apply the value to the memory address value to the bus, address bus, and then timing and control will issue read signal again for the second time. Okay, so now if you address has been applied and then after some time the control bus is issuing read signal, so again the second byte information will enter through the data bus from the memory. Now it again comes to the data bus inside 8-bit data bus, for example. Now where it will go? Now the question is, instruction register already is occupied with the first value. So it, and the second byte value is an companion instruction, companion information. So that companion information must be kept in one of the registers. Okay, so that data will not go anywhere else, but it will simply come to the register A, for example. Now, after these two things that came, first data came to the instruction register, second data came to the A. Data means from the program space. So for microcontroller or processor, it is just a value. And based on value, we are making some decisions. So based on the first value, it took a decision that after decoding, it took a decision that you need the second data. It performed whatever increasing counter, PC program counter, and then getting the second data to register it. Now, the point is what you will do with this data after it comes here. Now, the instruction that was originally stored in the first byte, if that says that you do the addition with, let's say, register D, whatever data is there in 0001, add that, for example, the meaning of the instruction that came up to be add that value with register D. So the second byte has come to A, and D may have something else from previous data, or it doesn't have any data, it may be just 00 initially. That is also a possibility based on how manufacturer designs this register initialization at startup. After you power up or at startup, these registers may have garbage value, or it may have been initialized to certain known value. Assuming register D is already known to be 0000, for example, just assume 0000. So, or rather 00 hex, I'll say, because it is an 8-bit register, because data bus is 8-bit. For simplicity, we can consider all registers are also 8-bit, instruction register is 8-bit, program counter is 16 bits, because you have 16 address lines. So after the second byte came and sat on the register, you have to do addition of A and D. What you will need? You need to first, you cannot do addition in this space. You have to take it to ALU, arithmetic and logic unit. So you have to copy the values of register A as well as the value of register D to ALU. You want addition of A and D. Your instruction said that you are having one companion data that came to A, but after that second data or byte came from the memory, you have to do the addition. So you have to again transfer from A to ALU, D to ALU. So there are internal steps which are required. So first clock cycle was elapsed in getting the data over here. Second clock cycle was used to getting data out to register A. Third clock cycle is utilized to get the data over here. Fourth clock cycle is used to take the and take it to the other input of ALU. And then the fifth clock cycle, you will possibly start addition inside the arithmetic logic unit. So in the fifth clock cycle, you will do possibly complete the addition, and then if at all you can complete within one clock cycle. Okay, typically addition takes more than one clock cycle. Assume it is very efficient and it is some sort of very well designed microcontroller. So ALU performs addition. After the addition result is available, where to store? That is another question. You have to store that data somewhere. So that data typically comes back to one of the registers. Typically, it overwrites the first register. Typically, not always, not in all microcontrollers, but in many instructions, you will find that one of the data inputs gets overwritten with the result of addition or subtraction. Okay, so that you'll find in many of the microcontrollers. So your A was having one of the data that came from memory originally, but after addition, during the sixth clock cycle, the result of addition came and sitting on the A register, overwriting the previous data. So that means registers are like random access memory. You can overwrite, read, write many times. Okay, so that's why registers can be considered as a part of the memory map. And then once you have the data in after the sixth clock cycle, you have the result in array. There is the task over? Possibly yes, but in reality, there are few last steps which remains. You have stored the result, but your addition may generate a carry, and you have added two 8-bit numbers. Register D was 8-bit, register A was also 8-bit value, right? So after addition of two 8-bit values, you may generate a carry. Where it will go? It will go, there is no space here, there is no 9th bit here. So that 9th bit, whether it is carry equal to 1 or 0, that will come and sit in the flags. So flags is a type of bit addressable register or memory location, you can say. Bit addressable. So in register A or B or instruction register, all 8 bits are written or operated at a time. You cannot do bit after bit most of the time. Most of the time. Not always, I am saying. But most of the time, you have to deal with all 8 bits simultaneously. So that 1 bit carry which got generated as a result of addition, that requires to be stored from the through the data bus. It goes over here to the flags, or internally you can actually update bit by bit. You don't need 8 bits together. You can have 1 bit at a time and just update. After addition, the carry goes to the one of the bits in the flag register. So flag is something like indication. So it indicates whether your carry has been generated or not, or also it has other indications. We'll see something like all results are 0 or not, all results are 1 or not. There are different types of parity checks which could be possible after the addition or whatever operation ALU performs. So it flags the way how the result looks like. So it gives you, without looking at the actual value of the result, let's say after addition you are getting some value which where all the bits are 0 or all the bits are 1 over here. So that kind of, instead of reading all 8 bits together or 1 byte together, just looking at 1 bit in the flag through another line of code, obviously, you can determine what was the previous result. So also Opposite is also possible. You have stored something in the flag due to your previous instruction. Now the second instruction is checking the flag and taking another purpose or another work through ALU. It may be logical work or it may be arithmetic work. Okay, so this is how a microprocessor functions in general. So this is a general architecture. I'm interested to communicate this because this architecture in its variations will come all again and again all over in its more complex versions in different microcontrollers. So this is a very root level, basic level explanation how a microprocessor works. So basically, whatever instruction comes, it decodes by using a large decoder, and once the decoder, any one of the decoder output is one or activated, then the timing and control takes over. It actually instructs remaining blocks when to store in flags, when to store in register. So once you're storing, reading and writing from register A or register D, you must be issuing some write and read signals, which are not shown obviously here. So those write and read signals for the internal blocks are also controlled by this timing and control. So I will say this timing and control, and in addition to instruction decoder, is the heart of any microprocessor. It is the brain also, you can say, that it basically takes necessary action. It instructs or rather it signals other blocks, even memory outside the microprocessor. Okay, so any questions over here, because this is very important.
Sir, is there a difference between registers and RAM?
Yes, there is a slight difference between a register and a RAM, which is very marginal but important. Registers are typically stored, is a type of SRAM. You can see registers are different types or same as SRAM, but stored inside the boundary of the microprocessor. So it's like it is staying within the microprocessor apartment. So it's a type of little RAM. But RAM, typically the standard RAM, SRAM, DRAM, NV, RAM. So those RAMs are consisting of large set of locations. That means there are kilos and megas and gigas kind of location. Whereas the number of registers is just 2 or 4 or 8 or 16 or 64 or very few actually, 100. So those kind of things. So very few number of registers are there, which are actually different, which is actually no difference, which has no difference than RAM, but the physical presence is very close to the this instruction decoder and all these other blocks. So it's a little SRAM which is present within the microprocessor. So in certain microcontrollers, they don't even call this as registers, not in 8051, but in certain other microcontrollers, they always call it as SRAM memories also only. So it is a type of SRAM only. There is no difference as such, but small in numbers and easily accessible by the microprocessor.
Okay. Okay, sir. Thank you.
Any other question? I'll drink some water. You can ask other questions as well. Have you understood what I said? This concept is very important. So you have to correlate or basically construct in your mind the relationship between the memory and the microprocessor, and within the microprocessor, how the things are going to operate.
Sir, like where is the memory initially stored before it reaches the register?
Please repeat the question.
Like where is the memory initially stored before it reaches the register?
Okay, so the memory is typically outside the microprocessor area of a microcontroller. So old computer system, in old computers, memory was a different chip, microprocessor was a different chip. As we also see in desktop and large computers, more powerful computers, we still follow that method. Memory is a separate chip or module or separate entity within the main box. In microcontrollers, in embedded systems, memories and microprocessors are fabricated side by side. They are actually fabricated side by side. Initially, microcontrollers, they used to fabricate two chips but in a same package. Something like you have one single integrated circuit package. Within that, there are two dies semiconductor chips or two semiconductor blocks having one memory and one microprocessor, or two memories, one microprocessor. But in modern scenario, we don't do that. We have technology to fabricate both memory and microprocessor side by side within the same silicon die. That means memory means what? A certain number of transistors. Microprocessor is also a certain number of transistors in certain with connections, some digital connections, obviously, all the time or most of the time. So they can fabricate side by side, make interconnections between them. So initially, the memory is within the same chip. Okay, initially means in modern microcontrollers, memory is within the same chip, but outside the boundary of the microprocessor. Why outside the boundary? Because the microprocessor is developed by a separate team of engineers. That is one of the reasons, actually, that memory engineers are different. Memory development engineers are different. They engineers, or they actually put different memories elements, different materials, like, as I said, magnetic nanoparticles or different types of low leakage systems or materials within the memory area. But the point is, the fabrication differences are actually nullified these days, and they can be fabricated just in a single run, single shot. Like I'm teaching all of you together. You are from some of you may be from different departments. In certain cases, I think some people from EE department has audited this. So it's like I'm merging you together. Same thing in microcontrollers. Memories are within the same chip. Does that answer the question, or the question was different?
Yes, sir, it answers.
Okay. Okay. So we discussed this. You can read this later on. ALU, arithmetic logic units. It performs different either arithmetic or logic functions. Program counter is just like a simple digital counter. It may be 18. It may be 16-bit or 32-bit. In 8051 that we'll study, program counter is 16 bits and ALU is 8 bits. And then instruction decoder. So the decoder, as I said, decoder is a large digital decoder which interprets the instruction that is fetched. One thing we discussed about fetching instruction, we discussed about decoding instruction, and then execution of instruction, right? Execution happens in the ALU. Okay, so fetch, decode, execute. So these three steps are always going to be present in very powerful microcontrollers like ARM and RISC-V these days. There is another concept of pipelining. Pipelining means once the first instruction is getting decoded, the second instruction is actually fetched and kept in the another instruction register or another register in between. So that is pipelining. So what is the pipelining? In certain microcontrollers, advanced microcontrollers only, that you are actually keeping a queue of instructions. So here in this architecture, we are bringing instructions, you are bringing data one after another. Then after we get all the information, the instruction itself, then the associated data, then only we start execution. So this is a sequential process. This is a slow process at the same time. Sequential means slow. I have to complete the previous one, then only I can start the next one. So that kind of method is followed here. So to speed up the process, people have came up with pipelining where they actually keep another register on top of this instruction register where they store the instruction, and then once the instruction register gets decoded, it automatically copies the value. over here. So as a result, you don't spend time for waiting purpose while the memory address control data will actually come, which takes some time, which takes at least few tens of nanoseconds in most microcontrollers. So even those tens of nanoseconds are very expensive or very slow. If you are executing a large program, very complex program, for that we prefer pipelining. That means there should be some internal queue of instructions that are maintained to speed up operation such that locally they can transfer quickly, but globally from outside the processor, from the memory, it takes longer time. So it does prefetch. That means before execution or before even decoding, it prefetches the instruction. We'll see that with ARM. So registers are something like SRAM, as I said, and it can be of different widths based on the microcontroller,
Sir,
either 8 or 16. Yeah.
even the
Tell me.
8-bit AVR have pipelining.
Yes. AVR is a RISC microcontroller. And
Right.
for a RISC microcontroller that came up after CISC variant, in fact, AVR came up to solve certain major drawbacks of 8051. So in 8051, pipelining was not present. So in AVR, that's why they introduced pipelining. But AVR pipelining strategy is very primitive these days, I'll say, because ARM and other processors are really outperforming and they're much more modern in even the pipeline design. So it's good that some of you have exposure to microcontrollers that I really like. You should always ask me such questions. I really encourage. And as a result, your question helps many others to get clarified. Even if I have forgotten or not came across certain things in future, if you ask such questions, I'll be more than happy to accept such question and I'll get that clarified, even if I cannot answer immediately. But for AVR, as you're saying, it's absolutely you should keep on asking such questions. Okay, so with that, I'll stop this slide and we will start with 8051. See, AVR is not there in our syllabus. So if I include AVR or MSP 430 or even some of the newer variant of ARM or RISC-V, I have to go through a very long bureaucratic process of approval of changing the syllabus. Okay, so I cannot do that directly. You are always welcome to read any other microcontroller as per your wish, but our syllabus is restricted to 8051, ARM, and 8085 to some extent. Okay, and there are 8086, but I don't cover that because there is no point in that because that gives you a complete different direction and also it takes a lot of time and it is not used in embedded computers these days. Most importantly, the purpose of embedded systems is not served by 86 series processors in general because they are very power hungry. They are very having complex instruction sets. Complex means very long and lengthy and quite difficult and a lot of things to remember. You have to mug up a lot of things. Rather, we'll only go through 8051 and ARM. And if you understand this two properly, I mean the entire class, not the expert students in the class only. The entire class should be able to grasp the concepts and you should be confident enough to apply for your applications. For example, I'll give you a little side story before going to 8051. Many of the IITs, even ISC Bangalore, came up with some indigenously developed microprocessor architectures and microcontrollers. So what is the objective? Why they are developing some new microcontrollers or processors? Because every microprocessor that we will come across will have certain drawbacks. Obviously, advantages are there. That's why they're popular. But there are some shortcomings that may be overcome. For example, today modern microcontrollers many of the modern microcontrollers are ultra low power microcontrollers. 8085, 8051, even AVR are not ultra low power. So certain variants are coming up from AVR series and PIC series from Microchip, which are ultra low power, and ultra low power uses sub-threshold digital logic. See, in digital circuits, we used MOSFETs or transistor BJTs. Typically, MOSFETs will consider only. Those MOSFETs are used in either cutoff or saturation. They don't used in triode region, typically in digital MOSFET circuits. But for ultra low power operation, people are exploiting triode region. Okay, because triode is actually used for typically analog in nature. There is a VI linear relationship, and that linear relationship is exploited. But as a result, there are basically different advantages. One of the advantages is low power. Another advantage is high speed operation. Okay, and that's a part of the triode region can be used as a sub-threshold logic. That means the MOSFET threshold voltage is never reached. Another side note I wanted to tell you, which is very important, again, if you want to go deeper, any digital circuit is analog in nature. I repeat, any digital circuit in this world is analog in nature if you look at it from inside, from in detail. How can I say that? I can give you an example. Remember noise margin in digital circuits. If you have forgotten what is noise margin, I'll quickly tell you. Noise margin is the range of voltages that could be considered at logic 0 and the range of voltages that could be considered at logic 1 at either input and output, and the difference between them. There are definitions and equations for noise margin. You can look at it. There are 4 equations in noise margin. So it is basically, let's say, voltage minus 0.5 to 1.5 volt, for example. I'm giving a just random example. So minus 0.5 to 1.5, that means range of 2 volt around 0 volt is considered to be logic 0. So logic 0 is not always logic 0 volt. Logic 0 could be 1 volt also, if the power supply is much more than 1 volt, obviously. If that if is again very conditional statement is important. If your power supply is 5 volt, then 1 volt could be considered as logic 0, and that comes within the that can be defined within by the noise margin definition. Also, 5 volt means logic 1. That's not always true. Exactly 5 volt is not possible. So you can maintain anywhere between 4 volt to 5.5 volt, for example. So 4 volt to 5.5, 1.5 volt range around 5 volt is considered to be logic 1. So that means those exact voltages could be 4.5, that could be 4.8, all those things. So those are analog voltages. So that means your transistors should be either in saturation or cutoff given that range of voltages are applied. So that means any digital circuit is analog in nature. So this is one way of looking at it, at my statement. There are other ways also. As I said, sub-threshold logic is another way, more modern way, where you never reach the threshold voltage. The MOSFET is always in triode kind of operation, and based on the exact voltage that you are getting for a particular input or output, for an input condition, the output will be again some sort of analog voltage, and then by using comparators or some sort of other digital logic schematic triggers, you can scale it to logic 1 or logic 0. That means again some other voltages which are more strictly defined. That means 5 volt means 4.8 to 5.2, not 4 volt to 5.5, something like that. So you have to always remember MOSFET basics are very important for understanding digital circuits in detail. But in typical industries, people don't consider this much because they are not doing research. We at IIT, we are doing always research in some way, in some capacity. So we should always go deeper in the technology. Okay, so enough of GAN. Now I will start with the next topic, which is 8051. Okay, so before I'll just open the slide, but I'll not use the slide initially. So let's go to Um, mm, Chrome. I'll open the datasheet instead. Okay. I will give a search of one of the decently improved 8051 versions. Okay, I'm typing 8089S51. So let's look at the datasheet. See, our syllabus is talking about 8051 only, but only 8051 is chip as such. The architecture is very popular even today. There are ultra low power versions. There are different modern microcontrollers even coming up in recent times, like 2020 or 2019. They came up based on 8051 architecture. The architecture was very powerful and very flexible. However, the original 8051, the original 80C51 or something like the old 8051 is obsolete these days. Basically, that chip is obsolete. The technology is not obsolete. The design is not obsolete. The concepts are still alive. But the original chip, the number that came up, 8051, is obsolete these days. So what I take generally, I take the approach of relatively modern and active devices such as 89S51. Okay, 899 means basically flash series of microcontroller. 51 basically that original 51 series, 8051's 51, and S means in-system programmable, such as if you have worked with any of the modern in-system programmable microcontrollers, you just plug into your USB port of the computer and program it. That is called in-system programmable feature or in-system programmable. So in-system or system level programming is used here. That's why S. So actually instead of 0, 9 is used because of flash version. So 8051 originally has only ROM. That means one time programmable, and even the most first, actually the very first version didn't had any ROM also. ROM was also outside, but number was same, 8051. Okay, so flash version S, and S means system level programming, in system programming. So this is an 8-bit microcontroller with 4 kilobytes of flash. So you can program the flash memory, that is non-volatile memory. I'll just zoom into it slightly and let's look at it closely at the features. So compatible to or compatible with MCS 51 products. MCS is microcontroller series. MCS microcontroller series 51 products. So 51 series was so popular and so unique and very useful at the same time that today also many modern, even much more modern controllers are using. Look at this endurance. As I telling, endurance is write erase cycles. So in this case, this is a slightly older one, which is featuring 10,000, but modern microcontrollers even feature hundreds of thousands, even millions of endurance. Operating range, this is the range of voltage. So there are 8051s which operate at 1 volt also these days. And static operation, fully static operation means basically it will be very stable and it will just perform as uniformly as possible over this entire frequency range, that is 0 to 33 megahertz. Typically, we don't count close to 0 in general because faster is better, but not always. Why they are kept this 0 hertz? That's one question. So if slower microcontroller is not so good, then there must be some other reason. The reason is that power. If you look at the equation for dynamic power consumption, what is the equation for dynamic power consumption? V square CV F C into V into F square equal to P dynamic. You can look at dynamic power consumption. So at dynamic, if you increase the frequency F, then it will also linearly increase the power consumption of this chip. So for certain operations, although this is not an ultra low power microcontroller, but for low speed operation, it consumes significantly less power. So that is the reason why they are going to few hertz. You can run it at a very low frequency, like 1 hertz. So it will take several seconds to execute just one single simple instruction. And there are different security levels, memory lock, and there are different basically layers of locking, because it gives security, such as you have developed a custom code as a part of a company or as a part of your own startup, and then you don't want other people to read your program whenever it is deployed in the market. So that's why there are multi-layered security system available to prevent copying of the memory. And then there is a RAM. There is only 128 bytes of RAM. Look, 128 into 8 bits internal RAM. You can use it similar to registers, but there are different registers also in addition to this RAM. So they kept those registers separate because registers are very close to the 8051 microcontroller microprocessor, whereas RAM is slightly away, which requires extra read-write cycles. Then there are 32 IOs, input output lines, which are programmable as input, as output, or an alternate function. So there are 3 ways for certain pins. But in AVR or MSP or ARM, you'll find every pin has alternate function for more than 4 types. That means you take any one of these 32, it will have 4 or 5 alternate functions. Based on the program, select any one and then operate or then run the code. In addition, there are timers. There are 2 timers or counters rather. This is different than program counter. Program counter is within this MCS 51 architecture, the microprocessor side, but this counter is separate counter for time delay calculation, for counting the objects, so those kind of things. For delay creation, let's say you are developing a clock, real-time clock, by using microcontroller, then these counters or timers are very widely used. You have to keep on reloading. They are up counting and down counting, or up basically incrementing timer or down incrementing timer. They can also generate interrupts after counting or timing. That means this counter timer is outside the microcontroller, microprocessor. It is within the microcontroller, outside the processor, something like memory. Memory is outside the boundary of the microprocessor. Same thing for timer. So once the timer serves this purpose independently, it can actually tell the microprocessor or within the chip that, okay, timing is done or counting is done, or what is the value of counting, by generating interrupts. Okay, so that's why this next is the 6 interrupt sources. There are hardware interrupts, there are software interrupts. So hardware interrupts means something coming through these IO lines. So programmable. Some pins are programmable as interrupt sources or inputs, and certain other interrupts are within, such as timers or other blocks that we'll see. Okay, so interrupts means what? A processor is running, and at any time, let's say I'm pressing a key from my keyboard. So a keyboard press can be an interrupt, hardware interrupt. So I'm making some changes in the external input device, and that device is going to tell the microcontroller that, okay, some signal has come, you need attention. So the interrupt reaches this microprocessor. Then there is UART port. UART means universal asynchronous receiver transmitter. So this is a serial port. The serial port is a bidirectional serial port with full duplex ability. Now, bidirectional means 2 direction input. It can take input, it can give output. That means it can communicate in 2 ways with an external device supporting this protocol, UART, universal asynchronous receiver transmitter. We'll see the timing and all details programming for this. You'll have that. You can start studying offline also if necessary. But full duplex is different than bidirectional. Full duplex means it can do simultaneous bidirectional communication. receiver transmitter. Okay, this indicates bidirectional ability. But duplex, basically that means it is also again bidirectional ability. Full is something that makes the difference. Full duplex means simultaneously it can do receiving and transmitting. That is for improved speed. Now there are some low power modes. It's like sleep mode. It's like sleeping the microcontroller. So you can keep the microcontroller in power saving mode. And also there are different power down modes or power saving modes in the sense that low power idle means it will not execute any code. It will go on becoming ready for operation, but it will stay idle. It will not execute. It will not operate the program counter and so on. That is for the microprocessor part of the microcontroller. But power down modes is related to more with the IOs, like memories as well as memories. So power down means you are slipping the memories, you are slipping the IOs separately based on your requirement. So processor can be on and power down can be activated for certain blocks. You don't need everything in the microcontroller all the time. So whatever you don't need, keep it in power down, and whatever you need, use the microprocessor or part of this chip. Then interrupt recovery. So suppose your microprocessor is sleeping, and then you can press a button and then you can ask it to come up from the interrupt or basically power down mode and then start executing. So it recovers from power down based on interrupt. Now watchdog timer. This is very important for operating systems with microcontrollers. So watchdog, why some people keep watchdogs or pet dogs? Because the animal is supposed to look at the intruder operations, or basically if someone comes in, the dog will bark and it will just alert, right? Basically, watchdog looks for any mishap or any improper or inappropriate operation or situation that might happen, like your program is getting hanged. That is also a problem. So the watchdog timer could help you to recover. So now I'll explain with the coding actually with more detail about the watchdog timer. We won't spend more time, but in general, we activate the watchdog timer in operating systems, and the watchdog timer keeps the track that you are not elapsing a lot of time due to any wrong code that is written in the program memory, or if the processor gets hanged due to some, it's waiting for an interrupt again and again, but it's not going to serve anything. In that case, this watchdog helps to recover. Okay, so through program you will see that. So it's a type of timer because it keeps track of time for how long the microprocessor is getting hanged up or it's busy with something else. So this timer is different than the previous timer that we had discussed. Then dual data pointer. So in 8051, program space and data space are different. So in the memory map, we have seen that the first few locations are reserved for program, and the later on we are using RAM and registers for data. So here in 8051, you can have, it's like two different program counters available. So one is data counter or data pointer, you can say. That's the more appropriate name which is used here. So program counter is looking after the addresses for the code memory, the program instructions, wherever it is stored. Whereas data pointer is equivalent to program counter or program pointer, which tracks somewhere in the RAM for data. Okay, and there are two such data pointers. Then flags, there are all sorts of flags. So they are only telling about power flag here. Later on you will see there are lots of flags which are there, which indicates carry, parity, zero, etc. And then there are fast programming time. You can quickly program in the matter of seconds. And flexible ISP programming, in-system programming. ISP is in-system programming. So this is ISP is a type of misnomer. ISP programming is a misnomer actually. P is actually program. In-system programming you can say also. So it is in byte or page mode. I was talking about page and segment sometime back with the memories. So page means a group of bytes, and segment is also means a group of pages. Okay, so something, these are related to organization of memory, how the memories are location are arranged. And then it is basically environment friendly options are used such that it doesn't operate with hazardous chemicals. Okay, you can read this separately. I will go to the pin diagram. So these are already there in the slides. So from the slides, it looks sometimes a bit boring, whereas from this real information from the authentic source, like this datasheet Atmel is makes more difference. Now I'll tell you something about Atmel. 8051 microcontroller was not developed by Atmel or Microchip or any other companies who have licensed, like even Texas Instruments, Renesas, and others. 8051 was originally developed by Intel. Intel in 1980s, in fact, late 70s, they started working on that. And then by very early 80s or late 70s, 79 or 80, they came up with the working chip, commercial chip. Like they're launching i7, i9 every now and then. Similarly, 8051 was launched during that time, around 41 years back. So Intel 8051 was very primitive and that was very power hungry. It used to get warm, but the processing power was very little. It was operating at only, I think, 2 or 4 megahertz. That was the maximum speed at that time, and that was considered to be incredibly high speed at that time. And later on, many companies found that this is an interesting chip. And today, the situation is opposite. Intel doesn't manufacture 8051 in general, but other companies have licensed the patent from Intel, and there are many companies who are even developing internal circuits while keeping the instruction set same or even extending the instruction set for this 8051. That's a little story about the history of 8051. Now you can see 8051 or 89S51. Here we are looking at S51 is a 40 pin chip, 40 pin DIP chip. So this is DIP means dual inline package. Again, VLSI engineering will tell you more about this DIP. And P means plastic. This P indicates plastic dual inline packaging. Earlier, 8051 was originally developed on ceramic, the old ones by Intel, because ceramic offers better heat dissipation because the chip was used to heat up. But today's microcontrollers have better circuits, better technologies, so not much heat is getting dissipated or generated. So plastic is good enough. Plastic is a bad conductor of heat, but that is good enough because it stays still with plastic. It stays almost cool as room temperature. Now there are different packages like plastic lidless chip carrier (PLCC), 40-pin 4-pin version. Also, thin quad flat pack packaging. This is the smallest among these three. Although 44 is there for PLCC, PLCC is a bit bulkier. TQFP is small, thin, quad, flat pack. Okay, so these are different versions of 8051 packaging from Atmel side. For different companies, there are other packages available as well. Even more number of pins are available than 40 or 44. Even less number of pins are available, something like 8-pin microcontroller version of 8051 with some other other name. And you can see there are different ports here. You can see port 1 here, port 1.0 until port 1.7. But actually, there are 4 ports similar to that. You can see port 3.0 to port 3.7 on the left side, port 1 and port 3. Whereas on the right hand side, port 0.0 to port 0.7 is one of the ports, and another port is ports 2.7 to 2.0. Okay, so you can think from generally I talk about it about port 0.7 to port 0.0, 1.7 to 1.0, because that's how is the standard way of representing the pins. And these pins are defined, this pin configuration is designed and defined by the manufacturer, in this case Atmel. And we have seen that some pins are programmable and multifunctional. That's what we can see that we'll see from this side. AD0 is the alternate function for 0.0, P0.0. And AD1 is the alternate function for 0.1 and so on. Similarly, instead of P2.7, we can have A15 function. Instead of P2.0, we can have A8 function. A series is address series. D series is data series. Okay, and AD means address cum data. So address and data both are merged together in this AD pins. So that means there are 3 functions for these pins. Either port 0.0, which is a digital input or digital output, and then address 0 or data 0. Okay, so any one at a time you can use it. Here, this TXT is for UART and RXT, TXT and RXT both are for UART. TXT means transmit data, RXT is receive data. Interrupt INT bar, INT 0 and 1 bar are the alternate functions for interrupts. These are external interrupt inputs. So these are inputs coming. TXT is the output line. RXT is an input line. But if you use that simple input output, digital input output, instead of UART digital input output, then this can be either input or output, any one at a time, obviously. T0 and T1 are the timer input and timer 1. Timer 0 input and timer 1 input. Write and read bar are the output signals. This is for accessing memory or input devices, output devices. Read, both are looking outside from the microcontroller. Write and read, these are control signals. Okay, int are the receive signals. RXT, TXT are the IO signals, UART IO signals. Timer is also an IO signal. Extal 1 and 2 are the crystal signals. So we need certain clock frequency. For that to happen, we need a very stabilized clock. The clock should be, the clock circuit requires an oscillator which is inside the microcontroller, whereas the oscillator requires a time base for accuracy, for very high accuracy clock in time. Suppose you want to generate a clock or watch for looking at the time. For that, your stability of the oscillator should be very important. It should not have deviation with time and temperature. So for that to happen, we have to connect an external crystal. So crystal oscillators are typically adopted in 8051 and many or most of the microcontrollers. The crystal part is outside, which is a separate device. It's a type of capacitor, such as quartz crystal, and the circuit for the oscillator, crystal oscillator circuit is inside. VCC and ground are the 2 power lines which are diagonal to each other to prevent short circuit. Okay, so today's microcontrollers are having much smaller in form factor or size, but earlier people were aware, were not able to make smaller packages, so they were also using thicker wires, so there was a chance of short circuit. That's why diagonally opposite connections are kept for power. EA is external access bar, as I said in one of the slides earlier, and VPP is programming voltage. So this is new. VPP is a programming voltage. This is a voltage for flash programming. So the flash memory, that 4 kilobyte flash that we had seen earlier in the first page, right? This 4 kilobyte, if you look at this 4 kilobyte flash, 8-bit microcontroller with 4 kilobyte flash. So that flash requires to be programmed. That 10,000 times programming is required. For that to happen, you have to apply 12 volt here. So this chip works at 5 volt. I'll just stop in just a couple of minutes or 1 minute. But during programming the flash, you need 12 volt here. That is an input pin. And external access bar is the output direction. VPP is the input direction for the microcontroller.
Sir, but
ALE is at
the
yeah, I'll stop.
ISP protocols does not require a 12 volt line, no? It only requires these four lines.
Yes. So there is a on-chip DC to DC boost converter in Avian or modern other microcontrollers that doesn't require 12 volt. But in traditional 80S51, this 12 volt is required, or higher voltage. This 12 volt for 5 volt versions. For 1 volt version, this is I think around 4 volt or 4 point something volt. So this high voltage is definitely required for flash programming because of FN tunneling process. This is a physics phenomena, Fowler-Nordheim tunneling. You will read that separately if you're interested. So FN tunneling is a method of storing data in the MOSFETs in the flash memory, and that requires an extra voltage, high voltage, for excessive electric field during writing process, okay, or deleting process. So that is why this high voltage is required. Modern microcontrollers have DC to DC converter inside the chip, so we don't care about that from outside. Even this pin doesn't exist, okay, in other ISP microcontrollers. ALE is address latch enable, and program bar is basically something input, which is a pulse that comes during the programming of the flash memory, and otherwise ALE is output line going to the memories or IOs. And program store enable is basically an output signal which gives the, if you need more memory space for code, more than 4K memory, then you can use external code space also, external flash memory or EEPROM, and there you need this PSEN bar. Okay, this is an output signal. So with that, we'll stop here today. I think we have taken a little more time. I'll quickly take attendance and then you can leave. Okay, so you can leave if you want, if you have other classes, or you can stay back and ask me questions.